Hello, 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 everybody, and welcome back. Welcome back. We're looking at C3 on our 2014 Canadian Open Challenge paper. Alright, so hopefully you've given C3 a try, maybe even C4, but that'll be for the next video. And we can dive in together and take a look. So what have we got for C3? So, a local high school math club has 12 students in it. Each week, 6 of the students go on a field trip. How very nice for them, how very costly for the high school. Although we didn't even have a math club in my high school. We had like 2 of us who were good at math contests. But that's okay. Alright, so we've got A part. Jeffrey, a student in the math club, has been on a trip with each other student in the math club. So there's 11 other students. He's been on a trip with each of them. Determine the minimum number of trips that Jeffrey could have gone on. Okay, so 6 students go on a trip. Let's suppose Jeffrey goes on a trip, and we've got Jeffrey named. We could have A, B, C, D, E, F, G, H, I, J for Jeffrey, K, L will be the 12. So could we find bus trips with Jeffrey and 5 other people? Well, kind of naively we could say, well, suppose Jeffrey goes with these 5 people on the first trip. Let's use a different color. These 5 people on the next trip, and then I guess L for Lisa. Lisa was the other good math contest person when I was going through high school, actually. So if you're watching, Lisa, hi. But Lisa sort of gets left out, and so we do require a 3rd trip there. Now, that's just sort of naively putting it together. I think this is probably the best you can do, just because we don't have any overlap. But it's a C-part question. We can't just say 3 trips and we're done. Unless they said something like it's 2 marks or something over here, and then you might be able to get away with saying it's 3 trips with an explanation like this. So let's look for something a bit more that we can say. So there are 11 students, and if J for Jeffrey is on a trip, that leaves 5 spots open. Now, to divide 11 people into groups of 5, you'd say something like 11 over 5 is 2 1/5, or I guess 2.2. So we need at least, I'm going to use floor function notation, or not floor function, ceiling function. This just means the greatest integer, or the least integer greater than or equal to the number. So 3. We need at least 3 trips are needed. There's no way to divide 11 people into groups of 5 for these trips that has at least 2. So you could just, I mean, you don't need to use the ceiling function. I just like throwing it in there whenever possible. But this is and you don't need to explain this notation or the floor function notation if you know what that is. The people marking these things have seen it. But because it's not an even division, if it was 10 people, then you get an even division of 2, and you might think that, oh, there's 2 trips that you could make, and indeed, if there were 10 other people, you could do this in 2 trips. But we've got 11 people, and so that 1 extra person, Lisa, left out, that's okay. So we have 3 trips are needed. Now, obviously, you could have lots of overlaps, and lots of ways to do the 3 trips, but you do need at least 3 trips. Now, just saying that we need at least 3 trips does not mean anything. You actually have to show that 3 trips is, in fact, a possible way to do this. Because, you know, some division and some rounding might show you that maybe 2 trips could be done. Like, obviously, it can't for this one, but just hypothetically, you could mathematically say there's 2 trips could be possible. But when you actually try and arrange the seating and things like that, suddenly you might find that actually there's no way to do it, and you need at least 3 or something like that. So half of the question should be, tell me why 3 is the least, and then actually show me that 3 will work. Okay, there's what's necessary and then what's sufficient, and then these are sort of more advanced math logic concepts. But so now I'm just going to say if our students are A, B, C, D, E, F, G, H, I, J, K, L, we could have first trip, second trip, and third trip. So Jeffrey needs to be on each trip. And we'll just sort of naively fill it up. A, B, C, D, E, F, G, H, I, not J, so K, L. And then we need 6 people, so why not let Abby, Beth, Colleen, and Dustin go again, I guess. Okay, that's so we could have so 3 trips will do. But we know we can't do it in 2 trips because there isn't a way to divide the people up. Okay? So that was A part. Now what about B part? If each pair of students have been on at least one field trip together, determine the minimum number of field trips that could have happened. So again, we're going to have to look at this mathematically. I assume set up a similar sort of division expression involving the number of pairs of students and field trips and things like that. And we'll show that, the minimum might be 10. I don't know. The minimum might be 10. Mathematically, 10 is the smallest number. But then we'll have to actually show that 10 trips you can get all the pairs to fit in together and things like that. Okay, so it'll be sort of two parts to this. All right, so each pair of students have been on at least one field trip together. Well, that's sort of what we did in A, though. Jeffrey was our singled out student. Okay, so the 3 that we learned of in part A actually has meaning in B part here. Let me see if I can put this together properly. We saw in A that for a given student, we need at least 3 trips. Okay, now we've got 12 students. Times 3 trips, so you might think the answer is 36, but we're counting each student twice. Yes? Because we're not looking at, we're each student could either be the student that we're looking at, the given student, the Jeffrey, or the student could be, the Lisa to another student's Jeffrey, that sort of a thing. So divided by 2 students in a pair. Okay. So let me just think about this. Does this reasoning work out? So we've got 12 students. So each student, Alice and Barry, all the way up to Jeffrey and Kevin and Lisa, each of them has to be a part of 3 trips. Because otherwise there's no way, if they're only, if Kevin's only on 2 trips, then I guarantee you Kevin has not been on a trip with every single person. So each person gives us 3 trips at least, 12 students in total, but each student is counted twice for a pair. So if we're talking about Kevin and Lisa, let's say. So to satisfy Kevin being on a trip with each student gives us 3 trips. To satisfy Lisa being on a trip with each student gives us 3 trips. But in doing these Kevin trips, we've counted Kevin and Lisa together at least once. And when making these Lisa trips, we've also counted Kevin together here, because we're not sort of counting an overlap or anything like that. So we have to divide by 2 students. Viewing once having the student as our singled out student, our Jeffrey from part A, and then having that same student be part of the innumerable horde of other students that our singled out student must be paired with. So So that's why we have to divide by 2. And I needed to sort of talk that out for myself there. So that should be 36 over 2. That should be 18 trips. Will be needed. Okay. Right. Or should we divide by something like 12, choose 2? Alright, if I doubt this 18, which seems a little high, but yet not that high, so I'll come back to this, but, okay, how can we try and do this? So A, B, C, D, E, F would be a nice first trip. Second trip, we could do G, H, I, J, K, L. And so now, and we might want to list the pairs out, but that's going to be 66 pairs. But, you know, if we need to, that's what we do. Now, let's think about a third trip. Now, A hasn't been with G, H, I, oops. Why do I keep writing J? I. J or K. A also hasn't been with L at all. Okay. Now, while doing this, we might think, well, gee, now you're using G and H together, so is there a more efficient way to do this? I'm not entirely sure. Now we could have L be with B, C, D, E, F. Still don't have L and A together, which is not good. But I'm definitely thinking that we might need... There might be another way to view the question. And so I think 18 trips is actually getting a little high, but... let's see. So A has matched up with everyone except, well, actually let's get A and L together. There. So now A has been with everyone. And we can get B, C, D, and E. Now they've been with L. I'm trying to be as efficient as possible because the math is telling me 18, and I'm starting to think that that's too many. So I have to think, well, what's wrong with my reasoning? 11 students, 3 trips, 2 students in a pair. I feel like that's the 2 students in a pair is a bit much. Maybe it's 6 students per trip, I think. Yeah, even if I view this with units, 3 trips per student, and then 6 students per trip. So... that would work out to be 6 trips overall. Now, can I do it in 6 trips? Let's see here. Let's try and split these up. A, B, C. You know what this reminds me of? Oh, what is it? Kirkland triples or Steiner triples or something like that. So I need A to be with G, J, K, and L. And we could do D, E, F the same way. J, this looks like 6 trips, but what have we actually got going on here? So A has gone with B, C, D, E, and F, G, H, and I, J, K, and L. And let's say G has gone with H, I, J, K, L, A, B, C, D, E, F. So it really looks like it, and if we check, we should have each student only appears 3 times, which works out quite nicely. I also really like the pattern here that I just sort of broke these up into pairs and sort of shuffled them in amongst themselves like a deck. Let's pick another student at random. Let's say, let's go with Kevin. Kevin's with L, J, I, H, G. Kevin now needs to be with A, B, C, and D, E, F. But he's with A, B, C here, and D, E, F here. So it looks like 6 will do. Okay. So that works. That's probably not the only way to write it out, but there we go. So 6 will indeed work out. Is there a nicer way to write this out? Yeah, I think there is, but you could probably just have A, B, C, D, E, F, and these students are just going to all be with each other. G, H, I, J, K, L, and then A, B, C again, D, E, F, D, E, F again. Actually, that's basically writing it out the same way. Let's do it this way. So we'll sort of alphabetize these pairs. G, H, I, J, K, L. And 2 that start with D, E, F. And then 1 that starts with G, H, I. There, I think that's a much cleaner way to write it out, but there we go. Now, I'm a little upset with my reasoning here, but that just sort of goes to show you that, okay, I tried to math at it for a little while, and I was unconvinced by my number. 18 seemed way too big to be experimenting with, and especially when I started trying to actually write it out, I found that 6 trips weren't so bad. Now, you might say I need to go back and justify my reasoning a bit more, and absolutely. Absolutely, that might be the case, especially for some of you who found the reasoning to be kind of flimsy. But yeah, 6 students, and we know, 12 students, and we know each of them needs 3 trips. But each trip gives me 6 students sort of satisfied or grouped together. I wonder if this might actually be easier to explain if I understood binomial notation, because how many pairs have we got? We've got 12 choose 2, and each trip gives us 6 choose 2 possible pairs to work with. So that would be what? 12 times 11 over 2 divided by 6 times 5 over 2. The over 2's will cancel out. The 12 over 6 will give me 2, so we'll get 2 times 11 over 5. So that would be 4.4. So that would mean that 5 suffices. Can I do it with 5? I don't think I can. No, I'm pretty confident in this. I mean, there's a little bit of overlap, but So 11 over 5 is 2.2, and you multiply that by 2, you get 4.4. So now, there might just be a flaw in my choose notation reasoning. I'm much happier with the 12 students times 3 trips divided by 6 students per trip. But, Can we do it with 5? Well, 5 trips. Each of them give me 6 students. Each student requires at least 3 trips. So, A pairs up with people, and there's at least one person left in A's trip here that isn't in the previous trips with A. That's guaranteed. And then think about this person. They would need to be paired with everyone else. And that's fine. So there's going to be a person in one of A's previous trips that doesn't appear here. Maybe person B. And, you know, this is C, D, E, and F. That has to appear here with B. And this person needs a 3rd trip as well. They're not going to appear here with B, I don't think. Yeah, there should be sort of a way to force 6 trips. Something like that. Something like that. B could appear here. I suppose B could appear like that. Well, does that suffice? Well, D needs to be in here because D doesn't have a 3rd one. E needs to be in here because that doesn't have a 3rd one. F needs to be in here. And of course, J also is missing some. J doesn't appear with F. And yeah, so I'm confident the original reasoning was fine. And that it is 6 trips. And I shouldn't have brought choose notation into it at all because I think I just wasted 3 or 4 minutes of everyone's time. But there we go. 6 trips will suffice, and we've got some reasoning behind it. 12 times 3 over 6. Okay. So, nice question. I got a little fuzzy there with the counting argument. If you had a cleaner one, I would love to hear about it down below. But other than that, I think it's time we moved on to C4, finishing up our paper. So I will see you for more of our open contest in the next video. Ta-ta for now.